very good morning and welcome to this part 2 lecture on tensor transformations. Today in this lecture we are going to talk about the transformation of vectors, transformation of a second order tensor, and using that we will generalize the results to transformation of nth order tensors. So let's get started. So in the previous lecture we showed the transformation of unit vectors from the non-primed to primed coordinate systems as well as vice versa. So I'll write that relation again. Because we will be needing them for proving or showing the transformation of vectors and higher order tensors today. So a general vector V can be written as V1 E1 plus V2 E2 plus V3 E3. So we have split this into the three components, and we can also write the vector as V1 prime E1 prime plus V2 prime E2 prime plus V3 prime E3 prime. So this is the same vector, except that we have chosen another coordinate system to denote this. So let us draw the coordinate system for clarity. So as you can see, we have the black or the base coordinate system, the red or the primed or the transformed coordinate system, which is obtained through a rotation, and the vector has been drawn using the blue arrow. So although the vector is exactly the same, it doesn't matter which coordinate system we look into, the physical vector does not change, but its components will change. So the components will be written as, so for the vector v in the base coordinate system, the components are v1, v2, v3, whereas the components in the primed coordinate system are v1 prime, v2 prime, and v3 prime. So we denote the components using a v prime, although the vector is still the same. So in some cases, sometimes we will write a v prime to denote the prime representation of the vector, but you must remember that it is only the components that change because we have changed the bases, but the vector as such does not change. So now the aim today is to be able to go from v to v prime using the transformation matrix A that we had obtained in the last lecture. So let us start the derivation. So we write the vector v as vi ei, and now what we'll do is we will go from ei to ei prime using the rule that we had just written in the beginning of the lecture. So that's rule number B. So we'll substitute ei as aji ej prime. So this becomes aji ej prime using B, and we will call this as C. Next we will write, so this is V. Next we'll write the V prime representation of the vector, which is in the prime coordinate system, which is given as Vj prime Ej prime. We're just choosing a different index, but that's a dummy, it doesn't matter, and we will call this D. So as you know, as you can see from here, that since V is equal to V prime, as we just talked about, so in that case C is equal to D. The right hand sides of C and D are equal. So from this we get Vi Aj Ej hat prime is equal to Vj prime Ej prime. Now since these are vectors, so the components have to be the same because we're talking about the same bases. So from this we get Vj prime as Aji Vi, and you can see that the second index of Aji is the first or the only index of Vi. So this looks some sort of a matrix multiplication. So let's write this in the matrix form. So V prime is A times V. So let me also write the complete matrix form. So this is A11, A12, A13 and so on. So this is our vector transformation law, which allows us to go from V to V prime using the information of the transformation, that is through the transformation matrix A. We can check, I mean, if we would want to check the initial notation representation, which is this one, this can be checked. So if you substitute j equals 2, so we have V2 prime, which is this one, as A21 V1 plus A2 V2 plus A3 V3, which is nothing but multiplication of this row with this column. So this works out, just to confirm that we have written the representation correctly in the matrix form. And just because it is common to use the index I on the left hand side, so instead of this one, I will make slight changes to it. So I'll replace the index j with an I and I with a j. So on the right hand side, we get Vj, and this Aji becomes Aij instead. So this is more comfortable to read. Otherwise, it is no different from the previous expression. So Vi prime is Aij Vj. So if I give you a transformation matrix or the information about the transformation, and I give you a vector, you should be able to get the components of the vector in or as seen from the rotated or the transformed coordinate system. Now what if you want to go back from the primed to the base coordinate system? So that is, if you have the components of the vector available in the base coordinate system, sorry, in the prime coordinate system, and you want to go back or find the components in the base coordinate system, how do you do that? Well, the inverse or the reverse transformation can also be obtained. So we can start with this V prime equals AV, and then what we'll do is we'll pre-multiply both sides by A transpose. So doing that results in A transpose V prime equals A transpose A V. But we know that A transpose A is identity because A is an orthogonal matrix, as we had shown in the previous lecture. So this is identity. So we get A transpose V prime is equal to V, or if we write V on the left hand side, this is V equals A transpose V prime. Or in the initial notation, we can write Vi A transpose Ij V prime j. Now since A transpose Ij is the Ji term of A, we can replace it with that. So this is the initial form of the vector transformation law in the reverse order. So if we have the primed vector components available, we can find the base or the non-primed components using this rule. So the only difference between this one and the forward transformation was that in the forward transformation, which is this one, you had a ij vj, whereas in this case you have an aji vj prime. So if you want to find v prime, it's a ij. If you want to find v's, it's a ji. I mean, it may seem difficult to remember this, but if you try problems, you will automatically get used to remembering this. Now that we have the transformation rule for vectors, the next step is to get the transformation rule for second order tensors. So the idea we'll be using is the following. So till now we know the transformation rule for vectors. We would want to utilize that to get a transformation rule for second order tensor. Now we know that the dyad of two vectors is a second order tensor. So we will form a dyad. We will then apply the vector transformation rule to the vectors in the dyad, and this will help us obtain the tensor transformation rule. I just want to mention this in passing that not every tensor can be written as a dyad of two vectors. It's easy to see that because a tensor has 9 independent components and two vectors will have 3 plus 3, 6 independent components. So representing 9 components in terms of 6 components is not possible always unless there is a special case. So please don't take it as that every tensor can be written as a dyad of two vectors, but we are using the idea of the dyad being a second order tensor to develop a transformation rule for second order tensors. So let's proceed with this. So the dyad or the outer product of two vectors u and v is given as ui vj, the tensor. And what we'll do is we will represent u in terms of u prime. So that's the reverse vector transformation. So ui will be written as a pi up prime. Similarly, the vector vj will be written as a qj vq prime. And now we write the initial notation for the dyad. So the dyad is ui vj, which in terms of the primed components for u and v can be written as a pi. I'll move both the a's on the left, aqj up prime vq prime. Now we will do some rearrangement to match the indices. So let's do that. So instead of writing API, I'll write this as the I comma pth term of A transpose. Then I'll keep UP prime and then VQ prime and then AQJ. So I want to see this as a matrix multiplication. So you can see that this index, the contiguous indices match and Q matches with the first index of A. So if I was to write this in symbolic notation, this becomes the outer product of the dyad UV, and then on the right hand side we have A transpose then we have u prime v prime, and then we have an a. And if we write uv as a tensor sigma, then u prime v prime is the prime representation of sigma. So this can be written as sigma equals a transpose sigma prime a. And this indeed is the transformation rule for second order tensors. In the initial notation, this can be written as sigma ij equals a pi a qj times sigma prime on the right hand side pq. So these are important rules because this is what we were hoping for to get. So let's give it some R and S as labels. So what R or S tell us is that if we have the primed components available and the information about the transformation to the transformation matrix, we can get the non-primed components of the tensor, second order tensor sigma in this case, using this transformation rule. What if you wanted, so this is some sort of a reverse transformation because you are getting the values of the base components of second order tensor sigma using the primed components. What if you wanted the primed components from the base components? So let's do that. So what we'll do is, in the expression R, we will pre-multiply with A and post-multiply with A transpose. And you'll see why. So if I pre-multiply with A, the left hand side becomes A sigma, and I post multiply with A transpose, so this becomes A transpose. Similarly, on the right hand side, we pre-multiply by A, then we have an A transpose sigma prime A, and then we post multiply with A transpose. So A times A transpose is identity, and A times A transpose is identity. So this becomes, if I write the sigma prime on the left hand side now, sigma prime is A sigma A transpose. And if we write this in the initial notation, so this is the I j component of sigma prime is A I P sigma P Q J Q, because you have an A transpose, so that becomes an A Q J of the transpose, so that's an AJQ. So we typically tend to write this as both the A's to the left, AIP, AJQ, sigma PQ. So since we had R and S, so this is T and U. So let's see the pattern here. So sigma was API AQJ. Let's go back and have a look. So sigma ij was API AQJ. So the I and J actually are the second indices of A, but if you are doing the forward transformation, I and J are the first indices of A. That's the only difference. So let's see from this pattern, can we develop a transformation rule for an nth order tensor? So let's use this expression U to do that. So let's say we have a tensor Cijk dot dot dot, and we would want to find the primed components, that is the components of this nth order tensor in the rotated coordinate system using the components in the base coordinate system. So let's see the expression U and see the pattern. So we have an A, and the first index of A is the first index of sigma prime. So in this case, it becomes the first index of C prime. This is AI. And then we have a new index because we'll have a C here with some P, Q, R dot dot dot. So this becomes AI, P. Then you have an A, J, Q. Then you have an A, K, R dot 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 times C, P, Q, R dot dot dot. So basically the number of A's is equal to the number of indices or the order of the tensor here, which is n. So you have a total of n A's, and the first index of the A is the corresponding index on the left hand side, and the second index is the corresponding index on the right hand side for C. So this is the pattern. And of course, if you're doing the reverse transform, the order of indices will change. So it will become an AP, PI, AQJ, ARK, and so on. So now that we have tensor transformation rule for nth order tensors, this is exactly what we desired. And this rule will help us figure out whether a quantity, a physical quantity, is actually a tensor or not. Remember, the transformation rule is the rule that is required for the quantity to satisfy for it to be a tensor. If the quantity does not satisfy the tensor transformation rule, it is not a tensor. So before we close this lecture, let's do an exercise to reinforce our understanding of this transformation rule. So here is a problem. The problem says that we have to find the transformation matrix A for the following transformation. So we have two parts, part 1 and 2. The first part is a 90-degree clockwise rotation about x1 axis, and the second part is reflection about the x1, x2 plane. Now we have talked about rotations, we haven't talked about reflections, but I just wanted to mention this because you should not take it as a fact that is this whatever we have developed, the transformation rule, that it only works for rotations. It does work for other kinds of transformations as well, except that for us in continuum mechanics, we mostly require the rotational transforms. So let's solve this problem. So this is our base coordinate system, and the transformation is a 90-degree clockwise rotation about the x1 axis. So if it's rotation about the x1 axis, then definitely the x1 prime is exactly the same as x1 because the rotation is about this. And then if it's clockwise, then x3 starts coinciding with x2, x3 prime, sorry, and x2 goes opposite, sorry, x2 prime goes opposite to x3. So this red one is our rotated or the transformed coordinate axes. Now what we need to do first is we need to find the transformation matrix A for this. So the transformation matrix components Aij are given as the cosine of the angle between xi prime and xj. So using this, let us find the transformation matrix components. So A11 is the angle between, or the cosine of the angle between x1 prime and x1. So x1 prime coincides with x1, so the angle is 0, so cos of 0 is 1. So A12 is between x1 prime and x2. So from the figure you can see x1 prime and x2 are at 90 degrees. So this becomes 0, and a13 is between x1 prime and x3, which is again 90 degrees. So this is a 0 as well. Then we have a21, so that is between x2 prime and x1. So this we can see from the figure is 90 degrees. So that's 0. A22 is the angle between x2 prime and x2, which is again 90 degrees. So that's a 0. And a23 is between x2 prime and x3, which is a 180 degrees. So that's a -1. Cos of 180 degrees is -1. Then finally, we have a31, that is x3 prime and x1, that's 0. And x3 prime and x2, they actually coincide, as you can see here. So that's 0 degrees angle, so that's a cos 0 is 1, and then a33 is 0 as well. So this is the transformation matrix for this 90-degree clockwise rotation about the x1 axis. Now the problem requires us to apply these transformations to a vector v and a tensor sigma, which are given as this and this. So basically we have to find the primed vectors and tensors using this transformation. This is a forward transformation. You want to find the primed components using the base components. So let's do that. So if you go back and have a look at the transformation rule for vectors, so a vector v is, so v prime, sorry, is a times v. We derived that as a part of this lecture. So this becomes 1 0 0, 0 0 minus 1, and 0 1 0 times the vector, which is 1 2 0. So if you do that, you get the vector 1 0 2. So this is equal to your v prime. So this means that v prime is 1 times e1 prime plus 0 times e2 prime plus 2 times e3 prime. Next is to find the transformed tensor components, that is to find sigma prime, and that we showed that this is equal to a sigma a transpose. So I'll let you do the multiplication. You already have an a, you can find the transpose of a, and sigma is given to us as this tensor. So I'll leave this to you to do the multiplication of these 3 by 3 matrices and find out what sigma prime is. So let's move on to part 2, which is reflection about the x1 x2 plane. So the x1 x2 plane is this plane, and if I reflect things about this plane, x3 axis goes down. x1 prime and x2 prime coincide with x1 and x2 respectively, but x3 prime goes down. Now with this reflection, our primed coordinate system is no more a right-handed coordinate system. It becomes a left-handed coordinate system because e1 prime cross e2 prime is minus e3 prime. And as I said, we don't really work with these coordinate systems in continuum mechanics typically, but we just want to show you that whatever rules we have developed, they also work for other kinds of transformations of coordinate systems. So the goal here is to find the transformation matrix A. So again, A11 is the cos of the angle between x1 prime and x1. Now we already know that x1 prime and x2 prime, they coincide with x1 and x2. So this is a 1. 0, 0 and 0, 1, 0. There's no change there, but x3 prime has changed. So A31 is the cos of the angle between x3 prime and x1, which is still a 0. x3 prime and x2, that again is 90 degrees, so angle cos of that is 0. And then x3 prime and x3, which is a 180 degree because it's flip, so this becomes -1. So this is the transformation matrix for a reflection about the x1, x2 axis. So all we need to do is we need to find v prime as a times v, and we need to find sigma prime as a sigma a transpose. Again, I leave this to you to do that and get the values for v prime and sigma prime. So this brings us to the end of this lecture. Today we developed the tensor transformation rule, which is a very important rule that allows us to get the components from the base to the prime or the primed to the base coordinate systems. In the next lecture, we will talk about the ideas of invariance and isotropy, which are very important ideas in relation to tensors. So thank you, and I will see you next time.